Hello and welcome to the Unit 12 podcast on Section 25.5. Today we're going to be talking about applications and effects of nuclear reactions. I'm Mr. Sakaguchi,
I am Mr. Lin.
and let's continue. Detecting radioactivity. Um, what's nice about radioactivity in terms of for its detecting, it does expose film the same way light does. Film exposures can provide quantitative measures of radioactivity. One way to measure dosage is through film badges. Most people who work in a laboratory or with radiation has to usually will wear a film badge or a film ring. I know when I worked with radiation, I had to wear a ring and a badge to monitor my exposure, and I'd have to turn them in once a month.
And those things are used to just make sure that people are having safe exposure levels of radiation. So if it's too much, then there's probably a leak somewhere.
And we'll talk about safe exposures and dosages at the end of the podcast.
Right.
Um, for certain kinds of radiation, some radiation is ionizing. Basically, when the radiation hits certain kinds of matter, it can cause them to become ions. And this ionizing radiation idea is the basis behind other detection systems, one of them being a Geiger counter, which you see below here with this little tube. You've probably seen them in the movies.
Right, that's the thing that clicks when you get near radioactive substances. And then you also have the scintillation counter. Same idea, except it's phosphors that are ionizing, so they tend to light up.
Yeah, so down here is your scintillation counter, and the computer basically counts the number of phosphors that ionize per unit time. For the Geiger counter, there's gas inside of this tube that ionizes, and that causes a change in electricity, which trips the meter here. Using radiation, we can use it for neutron activation analysis. What this does is it detects trace amounts of elements within a sample. We can also use it as a tracer. This was used early on in biology. It's not used as much these days because of the dangerous nature of radioactivity. Radioisotopes basically would be used we put it in samples and we follow where it goes.
So a way a radio tracer, for instance, would be used to be radioactive iodine, and they would use this to test for throat cancer, like thyroid cancer, because thyroid uses a lot of iodine, and if it glows unnaturally, then we know that the person might have thyroid cancer. Another form of radiation in use is the positron emission transaxial tomography, otherwise known as the PET scan. So what happens is positrons are emitted and they bounce off of objects such as your bones or certain differing densities of tissue, and the computer reads it, and we get a different readout on a person's body. And then lastly, we've got radiation therapy. This is used to kill cancer cells. In other ways that it's called is also chemotherapy in conjunction with the radiation therapy. And basically, it's because cancer cells metabolize and absorb things faster than normal cells. That means that it will also absorb radiation faster and kill itself, poisoning itself that way.
The biological effects of radiation, it's harmful to us over the long periods of time, so we want to minimize our exposures to radiation. The reason why it's harmful is because it ionizes molecules in the tissue, which can cause further damage. Free radicals can be created, and once these free radicals are present in your body, they're highly reactive and will start causing damage to your cells.
Free radical is essentially an electron basically it's a loose electron that goes flying around after it got hit by a radioactive ray or particle, and as a result it flies around and do things like hit DNA and knock a block of DNA off, and this results in somatic damage, which is damage to non-reproductive body parts, for instance skin cancer, okay, and it can also do genetic damage affecting your reproductive tissue, so your gonadal tissue would also be affected, and as a result could cause things like birth defects.
Or sterility.
Right. So no microwaving your burrito too hard.
Okay. Doses of radiation, radiation absorbed dose, or RADs, are measures of the amount of radiation that results.
So what you wind up doing is checking for the RADs, and these are multiplied over a factor of how much radiation energy is absorbed by the tissue, what kind of tissue, and how much exposure you've had. The product is the REM, when you multiply these together, which is the Röntgen equivalent for man. So in other words, the acceptable amounts of radiation that a body can absorb over a given amount of time.
Yeah, so for most of us who don't work with radiation on a daily basis, this isn't going to be an issue. But there are some people who work, who mine radioactive materials or work with them on a daily basis. So their exposures are very closely monitored, and if they if they've received a large dose or if they've maxed out their dosage for the year, those are problems for them, and they might have to be concerned with long-term radiation uh, uh, issues.
Notice in the chart below are different types of uh, excuse me, different types of radiation exposure. The scariest one actually is the one on the top of the list, which is radon. Doesn't happen very often, but sometimes there are pockets of radioactive gas in the ground, and they can leak out. So it's happened before where people are wanting to build a building, a house, or in one case a school, and they ran into a pocket of radon gas, and they had to evacuate the area and pump out the gas, make sure the area is clean afterwards, and then build on top of that.
And I think that's it.